Dear students, today we will be discussing about flat plate collector losses and loss estimation. Okay. So, what are different collector losses like side losses, bottom losses, top losses. So, these losses need to be estimated correctly, then only we can investigate the performance of a flat plate collector. Okay. As we have understand in the previous classes, like energy balance on the observer plate can be expressed by using this equation. Okay. So, Qu is equal to Ap into S minus Ql. What is Qu? This is the useful heat gain, right? Okay. Ap is the collector area or observer area, and S is the flux which is received by the observer plate, right? And this S is a function of these many parameters. Okay. So, IB into RB multiplied by tau into alpha for beam radiation, then ID into RD plus ID plus IB into RR, then as a whole it is multiplied by tau alpha for diffuse radiation. So, we understood how to calculate this tau alpha for beam radiation and diffuse radiation. We understand how to calculate this S. Okay. So, this part is now known to us, but in order to find out Qu, we need to know Ql. Okay. So, Ql is nothing but the heat loss from the collector. Okay. So, this Ql is a function of all the losses, like the kind of losses taking place from the top of the collector, from the side of the collector, and from the bottom of the collector. Okay. So, what I have shown here, it is a one glass cover and then observer plate. Of course, tubes will be there, okay, through which heat transfer fluid flows, right? And these are insulations. These are insulations. Some thickness you have to maintain. These are insulations. Insulation and these are insulation. Okay. This is side insulation and this is the bottom insulation in order to reduce the heat losses. Okay. So, this Ql, that is heat loss from the collector, can be estimated by using this expression if we know UL, AP and TP minus TA. What is UL? Is the overall loss coefficient, okay, and AP is the area of the observer plate, and TPM is the average temperature of the observer plate, and TA is the temperature of the surrounding air or ambient temperature of the air, right. So, once you know these values, then straight away you can calculate what is QL, right. So, as we understand, this QL is a function of other three losses. Okay. So, this QL is equal to QT plus QB plus QS. Okay. This heat loss from the collector is the sum of the heat loss from the top, heat loss from the bottom, then heat loss from the side. Okay. So, we can add it, right, and this heat loss or rate of heat loss can be expressed in terms of loss coefficient. If we express in terms of loss coefficient, then our expression will be something like this. Okay. So, Qt will be Ut AP multiplied by TPM minus TA, right. So, what is Ut? Is top loss coefficient, right, and for calculation of rate at which heat loss from the bottom takes place, then we use this expression QB is equal to UB multiplied by AP and then TPM minus TA, right. So, what is UB here? Is the bottom loss coefficient, right. Similarly, a rate at which heat is lost from the side can be calculated by using this expression where US is the side loss coefficient. Okay. So, as we understand, this QL is nothing but sum of all the three losses, that is QT, QB and QS, right. So, if we substitute this expression for QL, already you know UL multiplied by AP, then TPM minus TA is equal to, we have UT AP, this expression, then we have TPM minus TA plus UB AP TPM minus TA plus USAP TPM minus TA, right. So, these are common for all the cases, right. Heat loss is taking place, okay, from the plate to the ambient. So, these are common. So, finally, what we can write, UL is equal to UT plus UB plus US, or what we can say, if we divide the both side of the expression by AP multiplied by TP minus TA, so what we will get, UL is equal to UT plus UB plus US. Okay. So, what we have written here, this is nothing but the overall loss coefficient, right. So, this is very, very important parameter to measure all the losses, okay, and each value should be in the range of 2 to 10 watt per meter square per Kelvin. Okay. So, if this value falls in between this range, then our design can be considered. Okay. So, otherwise losses will be very, very high. So, under that conditions we will be losing our efficiencies. Okay. So, once we know this UL, then if we substitute in the energy balance equation, then from that we can calculate what will be the useful heat gain. Okay. So, we will demonstrate how this UL can be calculated by solving a numerical problem. Okay. So, let us have a look about UT or top loss coefficient. Okay. How to calculate this top loss coefficient. Okay. So, before we start the top loss coefficient, let us understand this thermal resistance network. Okay. So, here what happens, if we consider this is the plate, absorber plate at temperature TPM, okay, and this is at ambient. In all the cases it is ambient. Okay. This is towards top, okay, top, this is side and this is bottom. Okay. So, heat loss will take place from this plate to the sides, plate to the top, then this plate to the bottom. So, these are the thermal resistances. Okay. So, we can express in terms of thermal resistances. Okay. So, this component is the thermal resistance for the when heat is transferring from this plate to the bottom. Okay. This kind of resistance is offered, and here you can say the side, and this is along the top. Okay. And also what we can do, we can make equivalent resistance diagram. So, if we combine these three components, and we can make something like this, and it will be something like this. Okay. So, under that condition we can use what will be the UL, or if we know UL, then we can calculate what is QL. Okay. So, this is the equivalent thermal resistance network, right. The component what we have discussed in the last slides, these are represented in this thermal resistance network diagram. Okay. Now, let us have a look how to estimate top loss coefficient. Okay. So, this top loss coefficient can be evaluated by considering convection and radiation losses from the absorber plate in the upward direction. Okay. So, there are some assumptions while evaluating this top loss coefficient. What are the assumptions? First assumption is the transparent covers and the absorber plate constitute a system of infinite parallel surfaces. Okay. So, it is assumed that plates are infinite. Okay. And the flow of heat is one dimensional and steady, right. The temperature drop across the thickness of the cover is negligible. For example, if we consider this case, so here what happens, two glass covers are present and one absorber plate, right, and this is the sky temperature. Okay. Because of this, lot of molecules will be there like carbon dioxide, water vapor, they will also emit some kind of radiation. That kind of radiation is can also be taken care by using this sky. So, if it is thicker, okay, of course there will be it has got some thickness. Okay. So, there should not be any heat losses here. Okay. So, there will be no drop of temperature in those regions, right, here and then here, right. So, that is what it is said, temperature drop across the thickness of the cover is negligible. The interaction between the incoming solar radiation absorbed by the covers and the outgoing loss may be neglected. Okay. So, some radiation will fall here, it will go something like this. So, this kind of things are neglected. Okay. So, no losses are taking place, it is assumed. The transparent cover is assumed to be opaque. So, no radiation is going out, it is opaque to the long wave radiation. So, all the waves will be retained inside the collector system. Okay. Now, this heat transfer by convection and radiation, absorber plate and the first cover, if we are interested about from this plate to this plate. Okay. So, this is heat transfer by convection and radiation from absorber plate to the first glass cover. Okay. So, in this case two glass covers are considered, glass cover 1, glass cover 2. Okay. This is the absorber plate. Okay. So, in the first case what we will do, the kind of heat transfer taking place from this plate to the glass cover 1, we are interested to develop the equations by which we can calculate the rate of heat transfer. Okay. So, Qt by AP is equal to HPD is nothing but heat transfer coefficient from plate to the cover 1 multiplied by TPM, because this plate temperature is TPM, minus TC1. So, this is the temperature. Okay, TC1, heat exchange between this plate to this glass cover 1, and then radiation component has to be added. Okay. So, sigma TPM to the power 4 minus TC1 to the power 4, then 1 by emissivity of the plate. This is emissivity of the plate and this is the emissivity of the glass cover. Okay. Both the glass are of the same emissivities. So, since it is infinitely parallel surfaces, so we can use this expression for view factor. Okay. And if we are interested to calculate the rate of heat transfer from glass cover 1 to glass cover 2, then we have to use this equation, right. So, this HC1 to HC2 is the heat transfer coefficient, okay, and multiplied by TC1 minus TC2. So, since heat exchange is between these two plates, okay, and this is the radiative component and this is the convective heat transfer part, this is the radiative heat transfer part. Okay. And if we are interested to develop the equation or heat exchange between TC2 to ambient, then we have to use this expression. Okay. So, HW is the heat transfer coefficient when heat is exchanging from this glass cover to the ambient, and this TC2 is the temperature of the glass cover, then T sky is the sky temperature. So, please note that this sky temperature is different than this ambient temperature. Okay. This sky temperature is from those element which is absorbed in the atmosphere. Okay. And this part is the radiative component part. Okay. So, it has got two components, what is convective part and then radiative part. Okay. So, we have explained how this can be added and how this rate of heat transfer can be calculated, okay, between these parallel plates, right. Now, let us learn how this heat transfer coefficient can be calculated, right. If we go back to the last slides, so these heat transfer coefficients, okay, these heat transfer coefficients need to be calculated. Okay. So, in this expression, so our primary intention is to calculate this Qt by AP, right. This unknown is Qt and then TC1 and here is the TC2, right. So, Qt, TC1, TC2 are the unknowns, right. But this HPC1, this heat transfer coefficient, when heat is exchanging from the plate to the cover 1 and then from cover 1 to the cover 2 and then from cover 2 to the ambient. So, we can use some correlations to calculate these heat transfer coefficients. Okay. So, let us learn how these correlations can be utilized to calculate heat transfer coefficient between the parallel plates. Okay. So, Buschberg et al. Developed the following correlations based on the experimental investigations of natural convection heat transfer coefficient for the enclosed spaces. That means, between the absorber plate to the first cover and the first cover to the second cover. Okay. So, this correlations is something like that. So, if RA cos beta is less than 1708, then we will use Nusselt number is 1. Okay. So, if this value RA cos beta is in between this and this, then we will go for this correlation. If this Ra cos beta is in between these two values, then we will go for this expression, and then finally if this value is very high, then we will go for this expression. But we should be very particular about how to calculate the properties of the fluid. Okay? So, the properties are to be evaluated at the arithmetic mean of the surface temperatures. Okay? So, what does it mean? So, if there are two plates, they are having at say Tc1 and then Tp, then this fluid what is moving inside, so properties has to be calculated at Tc1 plus Tp divided by 2. Okay? So, after that only we can do the calculation, right. Also, we need to use other correlations for calculation of HW, that is heat transfer from the top of the glass to the ambient, right. So, this kind of heat transfer coefficient also known as wind heat transfer coefficient. Okay. So, McAdams correlations are something like HW is equal to 5.7 plus 3.8 into u infinity. This is nothing but u or v, that is velocity. Okay. So, we can write u infinity or v infinity, it is the same meaning, its unit is meter per second. Okay. Also, there are other correlations developed by Test et al. He has demonstrated based on his experimental observations that HW is equal to 8.55 plus 2.56 into velocity infinity. Okay. So, this is in meter per second. Okay. So, either of these two correlations can be utilized to find out HW value. Okay. So, if I am interested to calculate the sky temperature, then normally we use this correlation. T sky is Ta minus 6. Normally it is assumed that it is less than ambient temperature. Okay. So, Ta minus 6. Okay. If we deduct 6 from the ambient, then what we will get is a sky temperature, right. Now, let us learn how bottom loss coefficients are evaluated. Okay. So, this bottom loss coefficient is evaluated by considering conduction and convection losses from the observer plate towards downward. Okay. So, this way, this way this will come. And assumptions are flow of heat is one dimensional and steady, okay, and thermal resistance associated with conduction dominates. Okay. That is why convective part is neglected, right. So, in this case, if we know this thickness of the insulation, that is delta B, and then conductivity of the insulation, then straightway you can calculate what will be the UB. Okay. So, UB is nothing but Ki by del B, which is equal to thermal conductivity of insulation and then thickness of the insulation. So, if these two parameters are known, then straightway you can calculate what will be UB, right. So, once we are done with bottom loss coefficient, then our next attempt is to calculate side loss coefficient. Okay. So, let us learn how to calculate side loss coefficient. So, in side loss coefficient is estimated based on convection and conduction heat transfer. Okay. So, let us learn how to calculate side loss coefficient. Okay. So, these side loss coefficients can be estimated by considering both conduction and convective heat transfer. Okay. So, here also conduction resistance dominates and the flow of heat is one dimensional and steady. As we know, Qs can be expressed something like this: Qs is equal to Us multiplied by Ap Tpm minus Ta, right. So, here Ap we can calculate something like this. This area we need to calculate. Okay. So, this way we can calculate the area. Okay. So, if we know this L2 is the length and L1 is the breadth and H is the height. Okay. So, area will be something like this, because there are two sides, this sides and this sides, and also this sides and this side. So, all the things need to be considered. Okay. So, one important concern is here Tpm minus Ta divided by 2, this component is used. Why this component is used? Because see, if we consider this plate from plate, heat loss will take place something like TPM minus TA, okay, and this heat loss will be reducing slowly towards the top and then again towards the bottom. So, this average can be taken up, okay, the average heat loss can be taken up. So, that is why this term is divided by 2. So, average temperature drop across the side insulation can be considered something like TPM minus TA divided by 2. Okay. So, if I am interested about this US, then how we can do it? QS divided by AP multiplied by TPM minus TA. So, this is the expression, and what is the plate area? If we consider this L1 and L2 is the breadth and then length, then if we multiply these, then what we will get is AP, okay, what is written here. And this expression is known to us. If we substitute this value, then what we will have is nothing but US, okay. This US is nothing but the side loss coefficient, right. So, once we know this side loss coefficient, bottom loss coefficient and top loss coefficient, then we can calculate what will be the overall loss coefficient, okay. So, once it is done, then we can calculate what is QL, okay. So, once we know QL, then we can go back to our energy equation, then AP into S minus QL. So, this information is known to us, and once we know this, then what we can calculate is QU, okay. So, once we are done with QU, then we can do all those calculations or performance characteristics calculation, right. Now, let us take a very small problem. Say for a FPC with a top loss coefficient of 6.6 watt meter square per degree Celsius. If we are interested to determine the overall loss coefficient by using the following data, then how to do it? Okay. So, bake insulation thickness is given as 0.045, then insulation conductivity, or this is no thermal conductivity, this is not insulation conductivity, this is thermal conductivity, this is thermal conductivity, this thermal conductivity is something like 0.04 watt meter square per degree Celsius. Then collector bank length is given, collector bank width is given, collector thickness is given, then edge or side insulation thickness is given as 0.02 meter. Okay. So, how we can calculate this UB? Already we have the information, UB is nothing but Ki by del B. So, straight away you can substitute the values of thermal conductivity of the insulation. So, this is 0.04 and then thickness is 0.045, then what we will get is UB. UB is nothing but 0.889 watt meter square per degree Celsius, right. And US, we can apply the knowledge what we have derived now. So, US is something like this, then just we substitute the values here what is given in this problem, then we will get a value of 0.084 watt meter square per degree Celsius. Okay. So, since UT is given, this value is given to us, this is nothing but UT, then UL straight away you can calculate UT plus UB plus US. So, substituting those values what we have calculated now, so then what we will get is about 7.573 watt meter square per degree Celsius. Okay. So, as we understand, each value should be in between 2 to 10 watt meter square per degree Celsius. Okay. So, since this value is in between, then it is a feasible collector design. Okay. So, this kind of design is accepted, right. Now, let us take a somewhat bigger problem in order to understand the things very clearly. This problem has been incorporated in this lecture. So, example goes something like calculate the overall loss coefficient of a flat plate collector with 2 glass covers. Okay. We will have 2 glass covers and following data is given, size of the observer plate is given, then spacing between the first glass and then plate is given, spacing between the first and second glass is given, then the plate emissivity is given, then glass cover emissivity is given, okay. Tilt angle is given, and mean plate temperature is given as 73 degree Celsius, ambient air temperature is 25, wind speed is given as 2.7 meter per second, back insulation thickness is 10 centimeter, side insulation thickness is 5 centimeter, thermal conductivity of insulation is 0.07 watt meter Kelvin. Okay. So, we can use those correlations for estimation of heat transfer coefficient between the plates and the plate to the ambient. Okay. And also we can use the properties of air. Okay. So, to understand clearly, let us draw this figure first. So, we will have two glass covers, okay. These are two glass covers, and then we will have one absorber plate, okay. And we will have insulation, side insulation as well as we have bottom insulation. So, these are insulation, these are insulation, okay. So, this is given as 5 centimeter, okay. This is also 5 centimeter, 5 centimeter, and this is 10 centimeter, okay, in the problem, and this angle beta is given as 23 degree, okay, and AP plate area is given as 1.9 meter by 0.9 meter, okay, and this thickness is given as 5 centimeter, and emissivity of this absorber. So, this is a absorber plate, okay. This is an absorber plate, this emissivity of this absorber plate, I will write plate. So, this will be 0.85, and for these two cases, okay. So, emissivity will be, so this is C1 and C2 will be 0.85, right. And also it is given that TPM is 73 degree C, right. So, we can convert it to Kelvin. So, 73 plus 273.15 to be very precise. So, it will be 346.15 Kelvin. Okay. So, TPM is known to us now. Then what is TA, which is given in the problem, is 25 degree C, which is nothing but 25 plus 273, it will be 298.15 Kelvin. Okay. And also we know T sky temperature is nothing but TA minus 6. So, this expression we can use for calculation of T sky. So, T ambient is 298.15 minus 6, which will be equal to 292.15 Kelvin. Okay. This is T sky, this is T sky SKY. Okay. So, this value is also known to us, right. Now, what we want, first we need to calculate top loss coefficient, then only we can calculate UL, okay. Because first, if we are interested about UL, then what you need to do first, UT plus then UB plus US. So, all the three parameters are required. Okay. Let us first calculate this UT. Okay. So, the kind of techniques we are going to use here is a trial and error. Okay. It is iterative techniques. Okay. We have correlations to get direct result of UT, but no, first let us understand how this can be calculated by using this iterative technique. Okay. So, let us wrap this part, this is not required at the moment. So, this top loss coefficient, okay. So, our interest is UT we are going to calculate. Okay. So, in order to calculate this UT, what you need to know, this TC1 which is unknown for us, okay. TC2 is unknown for us, only known is TPM, okay. Then these values are known, this is known, this can be calculated by using correlations, okay. Correlations, by using correlations, and these two values are known, this is known, but this is unknown, okay, and this Qt we need to calculate. So, we will get 3 different nonlinear equations, and we need to solve for Qt by AP, right. So, let us proceed with the given data. So, what we can write here? So, HPCU1, then we have TPM. What is TPM? 346.15 minus TCU1 plus sigma value is known to us 5.67 into 10 to the power of minus 8, then TPM is 346.15 to the power of 4 minus TC1 to the power of 4. Okay. And for this expression HC1 to C2, then TC1 to TC2, these two are unknown. Then we have 5.67 into 10 to the power of minus 8, then we will have TC1 to the power 4, TC to the power TC2 to the power 4, and then these values are known to us. Okay. So, 1 by here is for plate it is 0.85, and then for glass it is let me check where is yeah, for plate it is 0.9, it is 0.9. Okay. So, this for plate it is 0.9, this is 0.9, and this is 0.85. Okay. This is minus 1. So, here we have 0.85, then plus 1 by 0.85 minus 1. Okay. And HW, then we will have TC2 is unknown, then T sky is known to us 292.15 plus, then we have sigma 5.67 into 10 to the power of minus 8 Stephen Boltzmann constant, then this value is 0.85, then TC2 to the power 4 minus T sky is 292.154. Okay. So, we can simplify it further. So, this equation maybe we can give is 1, and this may be 2, and this may be 3. Okay. So, what are those equations? These equations take care of the heat transfer, or rate of heat transfer takes place between this absorber plate to the glass cover one. So, I will write here cover 1, this is cover 2, glass cover 2, and this is TPM I will write, okay, or say I will write plate, okay, I write plate having temperature TPM, okay, this is at TPM, okay, this TPM value already known to us, okay. Now, our next step is to calculate this heat transfer coefficient, okay. So, we need to use appropriate correlation for calculation of this heat transfer coefficient, right. So, before we do that, we must know the temperature of TC1, but which is not given, okay. We need to assume those values TC1 and TC2. We need to apply our common sense, right. So, TA, if we write TA here, so TA will be how much is given 298.15, okay. So, this temperature what we got is 346, okay. So, 346 minus 298.15, it's about 48, right. So, it's half is 24. So, if we consider this value TC1, say let TC1 is equal to 328 Kelvin and TC2 is 306 Kelvin. Just we have applied our common sense, okay. So, this temperature is 346.15 and ambient is 298.15, okay, and then it is presumed that this should be somewhat hotter than this one. So, that is how we have considered 328, which is more than the average of this TA and TPM, okay, and TC2 is 306 we have considered. Just we are assuming this value, okay, because we have to do trial and error, okay. So, there will be two values of TC1 and TC2 which gives the same result of all the 3 expressions. So, once it is matched, then we can say that it is converged. Okay. So, this Tc1 and Tc2 we have assumed. Okay. Now, what we need to do for calculation of Hp1 means now heat transfer coefficient from plate to the cover one, then we need to take average of this Tpm and Tc1, right. So, this T mean will be 346.15, which is nothing but Tpm, plus we have this is Tc1 is 328, okay, divided by 2, which will give us a value which is equal to 337.075 to be precise in Kelvin. Okay. So, once we know this T mean, then we can get the data for air at this temperature, okay, because in between we will have airs, okay, no liquid is there. So, our tubes will be here. Okay. So, in centigrade it will be 63.925 degree C. Okay. Now, what we need to do? We need to use this property table. Okay. So, since this is at Celsius, okay, so we have 63, this value is in between here. So, we have to interpolate. Okay. So, to get the values of all, like no, we need Prandtl number, kinematic viscosity, then thermal diffusivity, conductivity, okay, all those values are required. So, if we calculate it, it is found to be nu is, that is kinematic viscosity is 1.9348 into 10 to the power of minus 5 meter square per second, and K is thermal conductivity is 0.02837 watt meter Kelvin, and Prandtl number is 0.7192. Okay. So, these values we can get from the property table. Okay. We must know that air is there in between these two plates, okay, no fluid is present. So, once we know these values, then what we need to calculate? We need to calculate the Rayleigh's number. Okay. So, let me calculate the Rayleigh's number. So, this R A cos of beta. Okay. So, R A is nothing but your Grashof number multiplied by Prandtl number, then we have cos of beta. Okay. So, this is nothing but beta this g delta t L cube by nu square, and then you have Prandtl number, because these values are known to us, and we have cos of beta. So, this beta this is nothing but 1 by T mean, what we have just calculated, at which we have taken the property data. So, this is something like 1 by, we have 337.075, this is for beta, and then gamma is 1.9348 into 10 to the power of minus 5. Okay. So, this is something like this. Then we have delta t 346.15 minus 328, okay, and length is given as, length means the distance between these two plates. Okay. So, this is 0.05, this is a characteristic length. Okay. And we have Prandtl number is 0.7192, right. So, this is found to be, and of course, we need to multiply by cos of beta, beta value is 23. Okay. So, if we do the analysis, then what we will get is something like 116,770.384. Okay. So, this value is for R A cos beta, right. So, now we have to apply the appropriate correlations. So, let us check which correlation can be used for estimation of heat transfer coefficient from observer plate to the glass cover one. Okay. So, let us go back and see this value, we should remember 116770. So, see, check 117670. So, we must use the correlation here. Okay. So, our value falls in between this range. So, we need to apply this correlation. So, this correlation Nusselt number is equal to 0.157, then R A cos of beta 0.285. Okay. So, since you have already understood what is Nusselt number and other parameters, then straight away you can calculate what is the heat transfer coefficient. Okay. So, this is nothing but H P to Cu1, okay, then multiplied by characteristics length L. Okay. This is K is the conductivity. So, 0.157, then R A cos beta is something like 116,770.384 to the power of 0.285. Okay. So, what will be H P C1? This value multiplied by K by L. Okay. So, this is something like 4.366 into K by L. Okay. So, this is found to be 2.477 watt meter square Kelvin. Okay. HPC1. Right. So, this K value is 0.02837 and this L is 0.05. Right. So, we can know now what is the value of HPC1. Okay. Now, what is next? We need to calculate what is HC1 to C2. Okay. So, for this case what we need to do? We need to consider this temperature and this temperature. Okay. So, already we have assumed that this TC2 temperature is 306. This is 306 and we have 328. Okay. So, what will be the mean temperature here? So, I will write it here. So, T mean will be 328 plus 306 divided by 2. So, which will give us a value of 317 Kelvin, right, and which is nothing but 43.85 degree C. Okay. So, this is the temperature. So, now properties of air need to be taken at a temperature of 43.85. So, just go back to this slide, this is 43. Okay. So, properties will be in between this 40 and 45. Okay. So, we need to find out the properties by doing some kind of calculation here. Okay. So, this is 43, right, this is in between 40 and 45. So, we need to apply this our principle interpolation. Okay. So, I will just show one calculation. So, if I am interested for say Prandtl number, so its variation is not much. Okay. You can take this average here. Say for example, diffusivity. Okay. If I am interested to measure diffusivity at 43, then what we need to do, 2.346 into 10 to the power of minus 5. So, you see it is increasing. Okay. So, then you have to plus. Okay. So, we need to differentiate it. This may be 2.416 minus 2.346 divided by 5 into 3, say 43 I am interested. Okay. So, that way we can calculate at 43 what will be the value of this thermal diffusivity. So, this kind of calculations we need to do for all the other parameters. Okay. So, at temperature 43, the values of thermal diffusivity alpha will be something like this. So, this is the way we can find out the values where these values are not given in the table. Okay. So, we use the appropriate values and we can do the calculation now. So, at these conditions, as per my calculation, so it is found to be nu is equal to, or kinematic viscosity is 1.7389 into 10 to the power of minus 5, okay, in meter square per second, and K is equal to 0.0269 watt meter Kelvin, okay, and the Prandtl number is equal to 0.7246. Okay. So, these values are known to us, then we can calculate what is R A cos of beta. Okay. So, this expression already known to us. Okay. So, beta this Z delta T L cube, okay, nu square, then Prandtl number, okay, then we have cos of beta, right. So, beta this is here 1 by T min. So, 1 by T min is 317, all should be in Kelvin, and multiplied by 9.81, and delta T is now between two glass covers. Okay. So, delta T is in between these two. Okay. So, this will be 328 minus 306. Okay. So, 328 minus 306. So, this will be 328 minus 306, right, and we will have nu square, L is again no distance between these two plates is 0.05 cube, and here nu square is 1.7389 into 10 to the power of minus 5. Okay. This is square and multiplied by Prandtl number. What is the value of Prandtl number here? 0.7246, okay, and multiplied by cos of 23. Okay. So, this is found to be 187710.11. This is R A cos of beta. Okay. So, this is known now. Okay. So, once you know this, then we can again see which correlation is appropriate for us. This is 187710. So, again the same correlations we need to apply. So, this value is also in between this range. Okay. So, same correlation you need to apply, right. So, correlation is here. So, HC1 to C2, then you have L by K is equal to 0.157, then 187710.11 to the power of 0.285. Okay. So, on calculation, so what value we will get is HC1 to C2 is nothing but 2.6889 watt meter square Kelvin. Okay. So, this value we got. What next we want? HW, right. So, how to calculate HW? So, already we know the expression for HW, which is also given here in the problem. So, HW is 5.7 plus 3.8 into U infinity. Okay. So, this is 5.7 plus 3.8 into velocity. Okay. So, these values are given 5.7 plus 3.8 into 2.7. Okay. So, this is found to be 15.96. Okay. So, this is watt meter square Kelvin. So, we know now HPC1 HC1, C2, then HW. Okay. So, now go back to our this expression. So, these values are calculated now, this is known, this is known, this is known, and these are the assumed values. Now, we need to check what is the value for this expression, what is the value for this expression, what is the value for this expression. If these values are not equal, then we have to come back to here again, and we have to select two values of TC1 and TC2, which gives approximately similar result of all these three equations. Okay. So, if we use now this equation 1, 2 and 3. So, if we use equation 1, then 2 and 3. Okay. So, already we have done it like QT by AP, okay, for this equation, and then QT by AP for this equation, then QT by AP for this equation. Okay. So, this expression is known to us. So, if you do the calculation, so what we have already I have done the calculation. So, if you substitute those values, then we will get something like this. Okay. So, if 328 was the first assumption for TC1 and 306 for TC2, then by using the equation 1 we will get this value 167.498, and by using equation 2 we get 176.803, and by using equation 3 we get 196.749. Okay. So, since the variation is very high, we cannot use this combination to calculate QT values, right. So, then we need to assume another sets of data. Okay. So, as per my calculations, what I have done, I have varied the temperature to 327 for TC1 and then 305 for TC2, and it is found that this approximation actually gives very close result. Okay. So, it is about 176.925, 175.391 and 175.293. Okay. So, these are very close. So, what we can do? We can take average of these three results. Okay. If we take the average, then what we will get is 175.869. Okay. So, this value we can take for calculation of QT by AP. Okay. So, this QT by AP will be 175.869. Okay. This will be in watt per meter square, right. So, what happens now? We will, this is watt per meter square, we will calculate what is UT. Okay. So, top loss coefficient that is UT is nothing but QT by AP, then you will have TPM minus TA, right. So, this value is 175.869 to TPM. So, TPM was 346.15 minus 298.15. Okay. So, once you do this calculation, then what we will get is the value for UT, which is nothing but 3.664 watt meter square Kelvin. Okay. This is UT. So, UT is done, then we can calculate what is bottom loss coefficient and side loss coefficient. So, for bottom loss coefficient, that is UB Ki by delta B. Okay. Ki is the conductivity of the insulation and delta B is the thickness. So, this value is 0.07 in this problem, and delta B is given as 0.1 meter. So, it will be 0.7 watt meter square Kelvin. So, U B also we have calculated now. Then we will calculate side loss or edge loss, side loss coefficient, that is U S is, we can use that equation L1 plus L2 multiplied by H, then we have Ki to the L1, L2, then we have delta S, right. So, if you substitute those values, L1 and L2 is 1.9 is the length and width is 0.9 and H is height is 0.2, and then we will have Ki is 0.07, okay. And then we will have L1 is 1.9 multiplied by 0.9 into delta S is given as 0.05, side thickness is 0.05. So, what is the height here? I will go back here to get this height. So, this is 5 centimeter, this is 5 centimeter and this is 10 centimeter. So, 5 plus 10 it becomes 20 centimeter. Okay. So, 20 centimeter means 0.2 meter. Okay. That is how is the height of the collector. Okay. So, this is nothing but the H. Okay. So, what we have to use for calculation of side loss coefficient. Okay. So, this is what we got, this 0.2, and once you do these calculations, then US is found to be 0.4585 watt meter square Kelvin. Okay. So, this US is something like this. So, as we know, overall loss coefficient can be defined as UL is UT plus UB plus US. Okay. So, if we substitute those values, 3.664 plus UB is 0.7 plus 0.4585. So, it is found to be 4.8225 watt meter square Kelvin. Okay. So, this is the overall loss coefficient which is in between 2 to 10 watt meter square Kelvin, which is recommended. Okay. So, our design is a good design. Okay. So, losses are not much. So, this design can be adopted. Okay. So, I will just briefly tell what we have done in this problem. So, problem was something like calculation of overall loss coefficient. So, in order to find out the overall loss coefficient, we need 3 parameters. One is top loss coefficient, one is bottom loss coefficient and one is side loss coefficient. These 3 loss coefficients are required to calculate UL. Okay. To find out this UT, we have adopted trial and error methods. Okay. So, we know the heat exchange between this plate to the glass cover 1 can be represented by this equation, and then heat exchange from this plate 1 to plate 2 can be represented by this equation, and then from plate 2 to ambient can be represented by this equation. It involves 2 components, radiative heat transfer components and convective heat transfer component, okay, in all the 3 cases. So, what we did first, we have substituted those values and we have identified the unknowns. Okay. The HPC1, HC1 to C2, HW, these are unknown and these were calculated by using standard correlations. Okay. And TC1 and TC2 are unknown for us, we have assumed it sets of values and we try to see the numerical values what we have received based on this assumption. If these values are found to be same for 3 cases, then that set can be considered as the final glass temperatures or cover temperatures. Okay. And also we need to find out the properties at the mean temperature of these 2 parallel plates. for all the cases. So, if we are interested about this, then we need to consider the plate temperature and then class cover temperature, then we have find out the values of T mean, and then we can get the air data from the property table, right. Then we can use it for calculation of these 3 values, right. So, we have done the calculations how this can be applied. So, once we know R A cos beta, then we must check which correlation to be used for this appropriate application. Then once we are finalized with that, then from that we can calculate what is HPC1, okay, and accordingly we can calculate what is HC1 to C2 and then HW. So, once you know this, then we need to check whether all are same or not. If it is not same, then we have to go back again and we have to consider a new set of TC1 and TC2, okay, and that will continue till we get a uniform result of QT by AP for all the 3 equations. Okay. So, first set of reading we got this, which are different from each other. Then finally, what we got is a very close values given by all the 3 equations. Then we have taken the average, and once you know these values, then straight away you can calculate what will be the top loss coefficient, because we know the expression QT is AP multiplied by TPM minus TA. So, heat loss is taking place from the plate to the ambient, right. So, these values are known to us and this is calculated, okay. From that we have calculated UT, then we have calculated UB, these are the standard equations. Then side loss coefficients we have calculated, then overall loss coefficients we have calculated, which are the sum of all the 3 losses or loss coefficients, okay. So, which is found to be 4.822 and which is fall in the recommended values, which is 2 to 10 watt per meter square per Kelvin, okay. So, that way we can calculate the loss or estimate the losses taking place in a flat plate collector, right. So, there are empirical relations available. So, without going this trial and error, we can straightway use some kind of established correlation to find out UT values of the particular collector, right. So, this correlation was developed by Klein, okay. So, this is a very long correlation and there are set of datas, okay. We need to check what is the value of TPM, that has to be in between 320 to 420 Kelvin. Then what is the ambient temperature? This ambient temperature must be in between 260 to 310 Kelvin. Then what is the emissivity of the plate? It should be from 0.1 to 0.95. Then what is the velocity of the wind, okay, and then number of covers, and then what is the tilt angle. All those things need to be in that range, then only we can use this correlation, okay. And one more correlations which is developed by Malhotra et al, okay. So, these correlations can also be used for calculation of top loss coefficients, okay, without doing the iteration method, right. So, we can summarize what we have discussed today. Primarily, we have discussed the heat loss from the collectors, what are different heat losses, and then heat loss coefficients like top loss coefficient, bottom loss coefficient, side loss coefficient, and if we combine all these losses, what we will get is a overall loss coefficient. We have also solved problems how to calculate losses associated with FPCs, okay. There are 2 techniques, one is iterative techniques for calculation of UT or top loss coefficient, or we can go for standard correlation for estimation of UT values, okay. So, I hope you understand what we have discussed today, and these are the basis of estimation of losses and which finally give the information about the performance of a flat plate collector. So, thank you very much for watching this video.